So it could be one of the hyperbolic trig functions then. All right, so I'm going to do a trig substitution. Theta, let's see, remind myself, the Pythagorean theorem says a squared plus b squared equals c squared. You found one? Which one do you think it is? So c, it is the inverse tangent, or is it the inverse tangent plus? No, that's different. All right, so c squared minus b squared, for example, would be equal to a squared. So this looks like my second version of Pythagorean theorem. So that means x has to be the hypotenuse. And then I'll make the square root. I'll make the 5 over here. 5 squared is 25. And I'll put the square root here of x squared minus 25. All right, so then let's see, from this right here, we're going to get, let's see, the cosine is 5 over x. So that means x equals 5 times the secant of theta. And so then dx, derivative of the secant, is the secant tangent, is that right? Secant theta, tangent theta, d theta. And the square root is 5 times the tangent, right? And we want the square of that, because we have no square root here. This looks familiar. I think we did this in class one day. But all these trig substitutions kind of blur together some days. Okay, so putting that back in, what do we get? I'm going to ignore the bounds of integration for now. We might trade them out. 1 over that x squared minus 25 gives us a 1 over 25 tangent squared. And I think I better shift this down to have room to write it out. Oops, missed. There you go. And then dx is equal to that long stretch there. So pen back, 5 times the secant theta, tangent of theta, d theta. I get that. I have my denominator. I have my x. All right. So cleaning this up, what do we get? We get one tangent to cancel, and we have a 5. So I have a 1/5, the integral of the secant of theta over the tangent of theta. Sines and cosines, yep, that's a good idea. All right, so let's try that. So rewriting this with sines and cosines, secant is 1 over the cosine. Tangent is sine over cosine, but we have the reciprocal of that, which is cosine over sine. Oh, that's cute. So now we have 1 over sine. Ooh, that's trouble. So I have 1/5, the integral of 1 over the sine of theta, d theta. Oh, and 1 over sine is just the, oh, is that cosecant? Oh, yeah. Cosecant's a pain in the butt, but I think I remember how to do it. Okay, so next, I'm going to do this the long way. Let's look at this as the cosecant of theta d theta. Now, my recollection from, let's see, what chapter was this? Chapter 8, section 2, was that we multiply by an interesting fraction. And I think the fraction we're going to multiply by is the oops, huh? Not, oh, don't tell me, don't tell me. Cosecant of theta plus the cotangent of theta. Let's see if this works. So I think this is the trick. Oops, I always want to put a CO in cosecant. So this is, I believe, the trick. So then if we multiply the cosecant through there, we're going to get a 1/5 times cosecant squared plus the cosecant cotangent. I wouldn't expect you to do this much work on a test, but you never know. All right, why, let's see, does this help us? What's the derivative of the cosecant? It's cosecant cotangent, is it, but negative? So I'm missing a negative. What's the derivative of cotangent? Negative cosecant squared. So the derivatives of each of these bottom functions are on the top, just missing the negative. So I can adjust for the negative by putting a negative in the numerator like that, and then multiplying by a negative outside. Now I can use a u substitution and say, let's let u equal our denominator. I'm just going to call it denominator, because guess what du is going to be? It's going to be the whole numerator. So du is going to be the entire numerator. Yeah, because the derivative of the cosecant is the negative cosecant cotangent. Derivative of cotangent is negative cosecant squared. So I'm not even going to continue writing it out in u's. This is essentially 1 over u. Integral of 1 over u is natural log, right? Now we still have that negative 1/5 hanging outside. So I have a negative 1/5 times the natural log of the absolute value of my denominator, cosecant of theta plus cotangent of theta. And then we're going to have that plus c hanging out. I'm kind of stuck with that 1/5. There's not much I can do with that. The negative, kind of stuck with that too. Putting it inside doesn't make things any better. So now we have to do a reverse substitution with our triangle. So let's do that on the next page. So let's highlight this. Control V. And then reminder for our triangle, let's draw that in over here. Our triangle said x was there, the square root of x squared minus 25 was here, and 5 was down there. So let's see, the cosecant is 1 over the sine, right? So that would be hypotenuse over adjacent. So the cosecant would be x over the square root. And then the cotangent is 1 over tangent, so that would be 5 over the square root. Did I get my trig functions right? I think so. And so we have that inside the absolute value, log of that whole thing, and a negative 1/5 out front. And oh, we had boundaries of integration, didn't we? Negative 2 to 2. Yeah, so we don't need the plus c anymore. I'm ready to say, hey, let's plug in our negative 2 and our 2. You know, that does clean up just a little tiny bit, so let's clean that up a little tiny. Oh, maybe it cleans up a lot. Let's see. Let's not do the boundaries yet. -1/5 is still hanging out. Actually, forget about the -1/5 for now. Let's just focus on the inside. That might clean up. Let's see. What do we have there? Common denominator, right? So that's x plus 5 over the square root of x squared minus 25. Now, x squared minus 25 is the difference of two squares, isn't it? So will it benefit me to rewrite this as x plus 5 over the square root of x plus 5 times x minus 5? Let's see. I would have to then think of x plus 5 maybe if I wanted to clean it up at the bottom. At least one way to do it would be to consider that to be the square root of x plus 5 squared. You with me? And then the x plus 5 in the bottom cancels with one of those in the top. I don't know if this is any better, but it looks like this blue sum is equal to the square root of x plus 5 over x minus 5. Oh yeah, that's kind of nicer, isn't it? I think I like that. Ooh, interesting. That's a problem. I'm thinking about the -2 here, and if we plug -2 in here, we get a negative inside the square root. That's trouble. If we plug it in here, we do not. So let's see, what is the difference there? I guess we had a sign, oh, right here. Yeah, we changed the sign of stuff right there. So this is only true if x is what? Is it just, no, it's got to be something to do with 5. So I think x minus 5 has to be greater than 0 for this to be true. So x has to be greater than 5. Yeah, so since we have a negative boundary, we can't clean it up that way. Question? Oh, that's still a negative there too, isn't it? Yeah. Oh, I guess no matter what, we have a trouble with that negative boundary. Huh. Let's take a look at the original function. What was I thinking there? Let's see, graph. Let's try Desmos today. And the original function was 1 divided by x squared minus 25. And that should be okay between -2 and 2. Zoom in there a little bit. I should get a negative area out of it. Interesting. Did I make a mistake somewhere? Because that leads to a problem also. Did I make a mistake in my substitution? Yeah, because for this to be true, you see something? The negative out front, if I bring it in here, takes the reciprocal of all of this. So if I take into account the negative out front, then I would be able to rewrite this as 1/5 times the natural log of the absolute value. If I view it in this form here, it would be the square root of x minus 5 over x plus 5. But -2 is still trouble here because I have the square root. Yeah, but the problem is the negative is inside the absolute, inside the square root, which means I'm going to get imaginary numbers. It depends on how you view absolute value. if you view, oh, can we get away with that here? Yeah, I guess, no. Absolute value of negative numbers is a bit more complicated than that. I don't know if you've ever seen natural numbers, sorry, complex numbers where this is the imaginary part of the number and this is the real part of a number. Did you guys ever see that in trigonometry? So if you have something like a plus bi, so for example, suppose we had 1 plus 2i, then you would go over here 1 and up here 1, 2. So that point right there in the complex plane is 1 plus 2i. And the absolute value of a complex number is the distance from that point to the origin right here. And that's what we call the magnitude of the complex number. Still says I'm live. Hello. Screen share. Start. Stop, bro. It still says it's broadcasting. I wonder what it picked up in between there. Let's see, where was I going to go? I wanted to take a look at our calculus book. Let's see, where did we first see hyperbolic trig? Section 3. Oh, no, that's 1 minus u squared. Oh, can I rewrite it the other way? We have u squared minus 1, essentially. I guess I could factor out a negative. If u squared, oh, okay. Yeah, this formula might help here. Let's see, why didn't I come up with that though? Oh, maybe I do have that. Let's see, I got another idea. Go here. Let's see, math, Parker, TH252. I started typing some notes for you guys. Uh-oh, oh, there it is. Other formulas, PDF. Oop, didn't print out very well. Looks like I need to edit these some more. Inverse hyperbolics. Oh yeah, there we go. This is supposed to say the inverse hyperbolic tangent right there, which is close to what we have. Yeah, so I think this formula is going to be useful. Where'd you go? So the integral, let me copy that into my cheat sheet here. Control T. Screenshot. This one right here. So we're going to manipulate this a little bit. Let's blow that up. Let's see if this gives, there's got to be a way to get that other answer to work out. So I got to think about that. Oh, yeah. Oh, I got an idea. Haha, Darren, you're so smart. Damn you. Okay, no, I think we do have an answer over here. Back this page over here, and we're going to work with this version right here. So, new page. So we've got 1/5 times the natural log of the absolute value. Now, our fraction is x minus 5 over x plus 5, right? But the square root, and this might be more cheating than we can do. We'll double check in a minute. The square root is the 1/2 power, right? I wonder if we can bend algebra by pulling that out. So we'll have 1/2 times 1/5, which is 1/10. The natural log of the absolute value of x minus 5, x plus 5. Yeah, we can definitely do this. I see it now. And the main reason we can do this because of the symmetry of the original function. It has even symmetry, right? So we could essentially integrate from 0 to 2. So I could have even done that before this, but I think this will work also because of the absolute value on our sign. With this version of the antiderivative, we can now integrate from -2 to 2, or double from 0 to 2. So I have a 1/10 hanging out, natural log, absolute value of x minus 5 over x plus 5. Oops, that's not a 5, is it? From -2 to 2. So this should be equal to 1/10 times the natural log. If we plug in 2, we'll get what? -3 over 7, which is going to be 3/7, minus the natural log of -7 over 3, which is essentially going to be 7/3. But wait, there's more. What is it? That's really a plus -1, isn't it? Times the natural log. The -1 can come as a power of 7/3. What's a -1 as a power do? It flips it, so that's really plus the natural log of 3/7. So in the end, we're going to have twice that. So we have 1/10 times twice the natural log of 3/7. Ooh, that was exciting. Thank you for asking about that one. So in the end, 1/5 times the natural log of 3/7 should be the answer. Now we cheat and whip out something like the integral calculator or Wolfram Alpha. What's your preference? What do you like? Integral calculator, how about you? That one too? Okay. Yeah, good job. Integral calculator, 1 over x squared. Did we ever get Gerald back? Oh no, we didn't get him back. Minus 25, close. Let's see, maybe I could try re-inviting him. All right. Oh, that the answer to this would be 1. Let's see if it freaks out about -2 to 2 or if it can handle it. All right, enter, right? And then it's thinking, what's that? What's that called? I don't know. Nothing comes to mind immediately, but I bet there is a term for that. All right, so they have a slightly different version of what we had. Oh, they split the division into a difference. Okay. Sorry, we keep losing you, Gerald. Okay. And so, oh, and they broke that up. Oh, they have the, let's see, the opposite. So if you switch those, yeah, so they'll get the natural log of 3/7 over 5, which is what we have. And if we double check, and again, according to the picture we looked at, it should have been a negative because the curve was under the axis. So double checking our answer, which was the natural log of 3/7, which is, since 3/7 is less than 1, we get a negative answer over 5, which is the negative 0.169, which is what the integral calculator agreed with. Ooh, that was exciting. All right. So, yep, gotta love Google. So backtracking just a little bit. So we were able to use a little algebraic cheat with natural logs by taking the square root as a power and taking that power as a multiple of the logarithm, which then we don't have a problem with -2. Other thing we could have done is realized right away that this was an even function, just integrated from 0 to 2 and doubled it. And so that also would eliminate the problems we were having with negative numbers. Question? Oh, we could have done partial fractions on this. Oh, let's do that next. Good call. Yes. This is so much fun. All right, so integral of 1 over x squared minus 25 dx, oops, is equal to, because the denominator factors, every time I see squares, I love trigonometric substitution. So I think it's way more fun than partial fractions, because I think I like drawing triangles. It's relaxing. So that's x minus 5 times x plus 5. Ignoring the integral for a minute, partial fraction decomposition says that something like this can be rewritten as some number a over one of the factors plus some number b over the other factor. Oops. And so we just have to find out what a and b are. So we multiply everything by the common denominator. Oops. Distributing that pair of factors to each term here, we end up with 1 equals a times x minus 5 cancels, so an x plus 5, b times x minus 5. And we can either combine like terms or pick convenient values. Anybody have a preference? Okay, convenient values it is. So first convenient value would be, say, -5. Then I can rewrite this as 1 equals, let's see, -5 wipes out the a term and gives me a b times -10, which means b must be -1/10. X equals +5. I don't know if you noticed, depending on the factors, these often tend to be opposite, so stuff cancels out. And here we're going to get 1 equals +5 is a times 10, which implies a has to be 1/10. Yeah, I suppose this might be a little bit easier than the, once you get past this point, then the trig substitution, yeah. But it could just look easier because we already did that other stuff. All right, so next, let's see, b is the negative, okay. So new page, we now have 1/10 times the integral of, let's see, I put the x minus 5 first, 1 over x plus 5 dx. And always double check here that you've got your a's and b's and factors in the right spot. If you mix them up, then you won't get the right answer. So double checking. I did have my x minus 5 under the a, and b was the negative. Since they both had a 1/10, I pulled the 1/10 out, just leaving the negative here. And now we are ready for an antiderivative. So 1/10 is hanging out. Antiderivative for 1 over x minus 5 is the natural log of the absolute value of 1 over x minus 5. Yeah, it is. That's probably the technique they applied, yeah. And then minus 1 over, oh, why am I writing it as 1 over? Incorrect. 1 over is up there, so this is just x minus 5. And this is x plus 5. Sorry about that. Now we have bounds of integration here, and I think what I'll do is go for the doubling, although I could do the other way, but so I'm going to say we have twice, oops, square bracket, from 0 to 2. So plugging in, let's see, 2 times 1/10 is 1/5. I guess it doesn't make much difference here. And then we're going to have the natural log of absolute value of -3, which is just the natural log of 3, minus the natural log of 7, and then minus again, parentheses, plugging in 0, I'm going to have the natural log of 5 minus the natural log of 5, which is 0. Yeah, so this part goes to 0. Natural log, because it's a number minus itself. All right, natural log of 5 minus natural log of 5 there. So then we just end up with this right here, which is, because of the minus between the logs is the same as what we had before, that's the natural log of 3/7. And then we have the 1/5 out front. Yeah, I think this was a little easier than trig substitution. That might be a good rule. When in doubt, partial fractions. I don't think integration by parts would work on this one. Yeah. Yeah, we haven't done with integration by parts in a while. Maybe we should do something with integration by parts. Let's see. Did anybody have another question they wanted to do? Yes. Number 8. Number 8. Number 8 I recorded on Friday. Yeah, so if you go back and look at the reviewed number 2, it's in there. I already did that one. Let's see, which one here would lend itself to integration by parts? E would, for sure. I would. No, I is just a regular substitution. J is a regular substitution. K is trig substitution. F is impossible. Just for fun. I was hoping people would recognize, oh, that's that crazy SI function. Let's do E. We haven't done integration by parts in a while. Okay, so integration by parts on number E. New page, 1E. We've got the integral of x squared times e to the x dx. And I think I didn't have any bounds. They were all indefinite integrals. Is that true? Yep, that section is all indefinite. Okay, so here we want to pick something for which the derivative u reduces and the integral dv at least doesn't get worse. So again, integration by parts says if you have something that you can break down as a u and a dv part, then that's equal to u times v minus the integral, switch them, v du. So I'm thinking u should be x squared, because then du would just be 2x, which is nice. So I'm going to let u be x squared, because then du is just a 2x dx. And then dv is going to have to be the rest of it, e to the x dx. And that's a nice integral. It's just e to the x. All right, so I've simplified through one step there. So then rewriting my black function, it's going to be u times v, which is x squared times e to the x, minus the integral of v du. So this and that, v du, sorry, bottom part. So that's going to be 2x e to the x dx. And then I look at this and say, guess what I need to do again? Integration by parts, because I still have something I don't know an antiderivative for. So I'm going to now say that I'm going to take the 2 with it. I'm going to say u is 2x, so I don't lose track of it. V, or dv, like before, is e to the x dx. So then du is just 2 dx, and v, again, is e to the x. Don't forget, we still have this x squared e to the x hanging out. And then minus, I'm going to put parentheses around all this to be careful, u times v, so that's 2x times e to the x, minus v du, which is just 2e to the x dx. Oops, I need my integral, sorry, dx. And distributing that negative, being careful here and there, I get black, sorry, x squared e to the x minus 2x e to the x. Negative times a negative is a positive. Integral of 2e to the x is 2e to the x. Yeah. And then I finally will throw in my plus c. Yeah, I did have a teacher like that once. All or nothing. Sorry, no C. It's minus 10. Oh, gosh. Yeah, breathe. It's not going to be like that. All right, that was exciting. All right, we are at a time for fun with math today, because I had check out the recording from Friday, and if that's not helpful, let me know. I'll fill in some gaps. But I think we did 2 of the 3 parts with an outline of how to do the second part. And we drew lots of pictures. Our final is tomorrow, right? Already Tuesday? Yeah. Let's see. We are a 11 o'clock class, so it must be at 10 o'clock. Does that sound right? Let me double check my schedule. Calendar. 10 o'clock is when our final is supposed to be, according to my calendar. Yep. If that time doesn't work for you, let me know. For those of you at outlying centers, I'll be sending that final